Hey everybody, this is 5.3, part 1, obviously, and it's, at least in this part 1, it's kind of like the pattern has been going. The part 1 portion is really going to be, the background, the algebra of the topic, before moving on to the calculus part. But so this is about polar functions, which perhaps you remember from pre-calculus. And maybe you remember, at least vaguely, that there was a lot of trigonometry that sort of got, there was like a callback to a lot of trigonometry when you did all that stuff with like polar functions and you were converting, you know what I mean? Remember, like when you were converting between like x and y and r and theta. Remember, polar is about r and theta instead of x and y, and there was a lot of trigonometry. Anyway, let's get going here. The start of this, I don't think this is in your notes handout, but just a kind of reminder about all these different SOHCAHTOA things, or the coordinate definitions. And so this picture would, I guess, potentially help you maybe do like the cosine of 90 degrees, or the cosine of pi over 2, or maybe the sine of 270 degrees, okay? Because you have all these coordinates on the unit circle, and the sine, for example, is y over r. So the sine of 270 degrees, or 3 pi over 2, would be negative 1 over 1, or it's right here, over 1, y over r. Now, I mean, I don't know if these pages are going to be that useful to you to reference, because you have your calculator and you're probably just going to go with your calculator. So I'll at least leave it on this little screen for a couple of seconds. Like, this would help you work with these angles potentially, with SOHCAHTOA. Like the sine of 30, for example, would be opposite over hypotenuse, or the cosine of 210 would be adjacent over hypotenuse. So I'll leave it on this screen for a couple seconds for these particular angles that are all sort of related to each other. And then this screen. But again, I think you'll just probably be more quick to go to your calculator, to like, if you needed to figure out the sine of 270 or the cosine of 0, I don't know, whatever. Or maybe you can do it mentally in your head. I mean, I can do a lot of that in my head, so perhaps you can too. But let's get started, okay? Like, officially, I suppose. Polar functions. Like I was saying earlier, if you remember working with polar functions back in pre-calculus, you should remember that there was a lot of trigonometry involved when you compared the x and y values with the corresponding r and theta values. So here's like some conversion type formulas or equations, or whatever you want to call them, identities, facts, whatever. But you can use these trigonometry type things to convert between x and y and r and theta. Like, if you had r and theta, you could figure out what x is, and you could figure out what y is. And now, if you had x and y and wanted to figure out r, you would use this. And if you had x and y and wanted to figure out theta, you'd use this right here in blue. And just maybe specifically solving these for r and theta, kind of like rearranging this so it was like actually solve for r or actually solve for theta. That's what that looks like. So yeah, I mean, this could almost be like the first draft, and this would be like the final version. Kind of like kind of like how these over here, they both started as something a little bit different and more recognizable. Like this one here in pink, you might recognize it better as the cosine of theta equals x over r. And the sine of theta here in maroon equals y over r. Anyway, I probably talked about that to death. Whoa! Looks like a lot going on here, but I mean, actually, that's only because there's like literally 4 examples on the same screen. Graph the points that are in polar form with the, okay, yeah, it says right here, with the given polar coordinates. Then find the rectangular coordinates. So I don't know if you remember from pre-calculus, especially if you had me, no offense to Birch, maybe you said this as well, or had something just as good to emphasize. What I say is when you're graphing these points that are in polar coordinates, start with the theta. Like find the theta value first, then plot the dot based on what the radius is. Because sometimes your radius is negative. So, I mean, again, what you want to do is find pi over 2 first and then plot the point based on the radius of 4. So that's all I'm going to really say. If you have any questions or need a more thorough reminder about all that stuff back from pre-calculus many, many moons ago, just let me know. You know where to find me. And so, you know, this guy, well, maybe I'll just do these literally one at a time. I was going to do all the dots, but so now when you go to find x, so that was going to be these 2 little equations. So you just kind of take your r value and your theta value and you do a little r cosine of theta. And like I said, this is where you probably are just going to grab your calculator unless you can do it in your head what the cosine of 90 degrees is. Like I know it's 0 in my head. Maybe you also can do that quick in your head with a lot of confidence. Like I was very, very, very confident that the cosine of 90 degrees was going to be 0 and so forth. Anyway, whatever. God, I'm like rambling so much. Y is our sine, so this is 1, I believe, and so 4 times 1 is... But again, calculator is obviously there if you need it. Example B, again, find the... maybe I'll talk about this one a little bit to help if you need. So you find the angle, which is pi. I was going to say theta, which is pi. And so you're on like this angle location, but since the radius is not positive 3 but negative 3, you end up there. Okay, even though like the angle was 180 degrees or pi radians, based on the negative radius you end up like back, okay, on the like on the opposite angle or whatever you want to describe it as. Same deal. I mean, all 4 of these examples are not going to be that different. I mean, I think the only reason there's 4 examples is to kind of throw at you all the different, well, what if it's a negative angle and a negative radius, or a positive angle but a negative radius, whatever. And it's always the same steps. And so 5 pi over 6, I'm not good at knowing. I mean, it's literally 5/6 of pi, so it's probably like right there, which I'm going to say is 1/150. Like I'm going to say it's, yeah, but you can go to your calculator and do 5 times 180 divided by 6, which is what I've done for most of the time over the years. But you know, you might look at that radian measure and just kind of know where it is. You know, like Birch, for example, I think probably groomed his students way better than I would have to like understand radians and kind of know them inside and out. But literally 5/6 of pi, and if pi is 180, then whatever. So it's the same steps. You can go to your calculator, whatever you got to do. Those are the answers. If you have any questions, let me know. But I'm not going to explain the same steps over and over again. So hey, remember this. I will slow down here. A negative angle, remember, what's the difference? Positive angles mean you go up and around from 0. A negative angle just means you start going down and around the other way. So negative pi over 4, that's negative 45 degrees. So you end up here. So positive 315 is coterminal. Remember that word? It's the same basically, in a lot of ways. Positive 315 is the same as negative 45. But then even once you're on here, it's a negative radius, and so you got to like kind of go to here. Well, pause the video if you need extra time. I'm moving on, so you might want to pause the video and write those answers down. Find two different sets of polar coordinates for these rectangular coordinates. And I think, like speaking of coterminal and stuff and things of that nature, that's why you're going to be able to find at least two different ways to give the same point with different polar coordinates. So anyway, with knowing x and y, just remember, I know you might still be brushing off the cobwebs from pre-calculus, but these are the formulas and equations you're going to be using to take x and y and figure out r and theta. So to find r, we're essentially going to use the Pythagorean theorem. And so we get r equals 1. And then to find out theta, we're going to have to do like the inverse tangent, which you can do on your calculator. Inverse tangent and, time out. Whether you have like a cheat sheet, like a little reference chart or something, or you're going off of your calculator, whatever, like let's say you're going on your calculator and you ask your calculator, like, what is the inverse tangent of 0? You gotta remember in like scenarios like this that there's technically like an infinite number of answers. There's technically an infinite number of theta values, angles, that if you take the tangent of it, you get 0. There's an infinite number of them. Now on the first go around, between like 0 and 360, like one revolution or whatever around the circle of angles, there's probably only 2. Okay? But so at least between the 2, like we have to pick the correct one, so don't just blindly go with what your calculator tells you. You have to, here we go, you have to look at the original coordinates, that it was like positive 1, comma, positive, or 0, I guess you can't really say it's positive 0. But it's 1, 0, which, does that put you at 0 degrees, or does that put you at 180 degrees? You know what I'm saying? So you got to make sure you pick the correct theta. And then I mean, it's just kind of what they're asking for is, okay, so you could obviously say 1, 0, or you could describe it as like 1, 2 pi, or negative 1, pi. I mean, there's a lot of different ways, and not even using like that much of a coterminal sort of dynamic. Look, a negative radius with just a different angle. I mean, there's all different kinds of ways to name like the same point, many different ways. And again, I don't think there's going to be this much difference. Just remember how to square a negative number. Don't make a rookie mistake, rookie. So we get this, simplifying square roots. See, once again, there's an infinite number of answers, but as far as what we're going to care about to at least start, there's really 2 answers. So don't just blindly go with what your calculator says. Here we're obviously in quadrant 2, which means we're going to go with the 135 and not the 315. And then just here's like at least 3 different ways to say the same point using polar coordinates. You know what I mean? Like this one's using a negative radius. I mean, whatever. This one's using something coterminal, like this is literally coterminal, just like this was basically. You can use radians, I mean, whatever. So that's what it means by two different sets, but it's basically saying the same thing. What? More examples? But why? Oh, look at this. Does not exist, but that shouldn't throw you off too much. Move that box. Is there anything worth noting about these third and fourth examples? I mean, okay. So, how do you find out theta? I mean, theta's kind of obvious, isn't it? 0, negative 4. I mean, so don't let like the fact that you got an undefined, thing here and finding theta, I don't think you'll get confused by this little plot twist. Like, the angle ends up being either 90 or 270. But it looks like based on these exact coordinates, we were going with the 270. I don't know. I don't think there's anything worth noting. Okay. I don't know how much I want to. I don't need to make too big of a deal out of this. I mean, you guys can literally. There's actually a mode, you've probably seen it, maybe even used it before in your calculators. There's a polar mode. Like you don't have to enter in your equation as y equals. You can enter in an equation as r equals. Well, look at this one. I guess not for this one. So what are we going to do for this one? But anyway, I'm not really going to put too much stock on these polar graphs for now, at least. But I mean, okay, think about it. What would the graph look like where you're trying to represent all the points that hold true with this equation, r equals 3? Like, what if you were to graph all the radiuses, all the radii of 3? Would you not just get a circle? Like, wouldn't this just describe that graph? And then negative 3, I mean, whatever, same thing, A negative 3 radius is no different as far as a graph, you know what I mean? And then what if you were to plot all the points that held true with this equation, that theta had to equal pi over 6? Like, what if you were to plot all the points where this was true? All the points where this was true. Wouldn't that be a line? And look, it's not just these, it's not just the positive radii for that angle, it's also the negative radii. So it's a line that goes off forever in both directions, not just there. Anywho, so like I was saying, you can get out your graphing calculator, or what was I going to do here? You probably know about Desmos. R equals the sine of 6 theta. R equals the sine. You type in SIN and it knows what you're talking about. And then, I should probably put a left parenthesis. And then you type in 6, and then here's how you type in theta. At least this is what I do. THETA. And it just knows it. Isn't that cool? So let me show you that again. I'll type the 6 again, and then THETA for theta. Like, you literally spell theta and it just kind of automatically does it. And we'll get into this next video. But and I'm zooming. That is like one of the coolest graphs ever. But so yeah, you can just use Desmos or your graphing calculator. Just you'd have to make sure you were in polar mode. It's like POL, I believe, polar mode. You'll find it. It's like the whole parametric deal. Same menu. And you know what? Just graph these if you want to. sketch the graph if you want, if you're kind of a completist like I am with your notes, like you don't want to leave anything blank in your notes. You can sketch a little graph. Show that the polar graph of r equals 4 sine of theta is a circle. Well, what was the lesson where I showed you? Did you already see a video like this? You had to have, because I'm doing this in order. What lesson was this? Ellipse. Is it vectors? Was it the lesson on vectors where I kind of sort of threw this at you out of nowhere? Where, you know, just in case you didn't know this from before this class, that this is what the equation of a circle looks like. So, I mean, this is just going to be algebra, people. And so, I don't know if you remember this trick from pre-calculus, you know, where I think what you were doing in pre-calculus in this situation, like the directions were just tweaked a little bit. Same type of problem, really. But I think the directions basically said, like, take this polar equation and convert it to a Cartesian, or rectangular, I guess was the word, a rectangular equation. So basically, rewrite this equation, but using x's and y's instead of r's and thetas. You know what I mean? And so this is the kind of thing you did. In this situation, you would have had to, like, multiply both sides by r to get the ball rolling. So what I did here was I multiplied both sides by r, and that way I can take this r squared and switch it out with what it's equivalent to, but using x and y, in terms of x and y. See that? And then r sine of theta, this r sine of theta chunk, you can literally switch out with just y, because y equals r sine of theta. And now you're cooking. And so that now this is rectangular in nature and not polar. But now you have to take this and, like, keep it going and keep messing with it until it's literally in this form. So here's what we got to do. Okay, we're going to move this 4y and hook it up with the y squared. Okay, and now what we're going to do is we need to take this couple of terms and somehow play around with it so that we can rewrite it as y plus or minus something in a bubble that's squared. So what we have to do is we have to take these two terms, okay, these two terms, figure out what the third term would be, because we basically need to have this be three terms that we can unfoil, that we can, like, factor, okay, and we can factor it into, like, bubble, you know, where it's like the same bubble twice, and therefore it's really bubble squared. So that's why what we're about to do is called completing the square. We're going to complete the square. We're going to figure out the mystery third term here that would make this binomial into a trinomial that we could factor into, like, two bubbles that are exactly the same. So what do you think that would be? What do you think that magic number would be that we would squeeze in here where we would now be able to, like, unfoil it, factor it into the same two bubbles? Well, plus 4. And you know, all you got to do is you got to take this middle term, cut it in half, and then square it. So what's half of negative 4? Well, negative 2, technically. And then when you square negative 2, you get positive 4. So we need to kind of include and kind of toss in there, like toss into the mix, a plus 4. But you're not allowed to just do that. You got to keep this equation balanced and, you know, really unchanged. And so whatever you're adding to, you know, here to complete the trinomial, complete the square, you have to also add to the other side. And so you get here, and now you can take this trinomial you've just completed and unfoil it into y minus 2 times y minus 2, which is y minus 2 quantity squared. And so with this written now in purple, you've shown that the polar graph is a circle. You know, where you're at, I believe, 0, 2 with your center. And the radius is 2, because, you know, radius squared is 4. And then just something else really quick before we end this part 1. You can take like a polar equation, right? R equals some function of theta. You know, like look, these obviously as well. You know, these are all, you know, R equals f of theta, R equals f of theta, R equals f of theta, you know, R equals f of theta. So if you have just some polar equation, you can define them parametrically, you know. So this polar equation, you can split up into like a parametric x equation together with a parametric, I don't know if I'm using the right lingo, parametric y equation. It's probably not correct, you know, lingo, but so all you do is you do, I mean, look, based on this, which, okay, yeah, we know that x equals literally r times the cosine of theta. That's what x equals, r times, we know this. Like, this is a great jumping off point, okay, but really it's this. So, let's go with, like, oh, I don't know, maybe just yellow. So that's really the punchline, okay? This is like a starting off point that goes like, oh, so what that really equals, since r is equal to all that, we're just going to say that x equals whatever that theta business was times the cosine of theta. And then same down here with y. So let's just see this in action really quick. It's so easy. If you wanted to define this polar equation and graph using like parametric equations, and so you could potentially graph it with you being in like parametric mode instead of in polar mode. Here we go. You just say that, well, I'll just give you the final answer. Look, x equals t, yeah, whatever, t theta, yeah, who cares? So x equals the sine of 6t times the cosine of t. That's all you do. You tack on a cosine of t. And with the y equation, you just tack on a sine of t to that. It's really easy. So what's this going to be, people? X equals what? Well, it's going to be this, you know, whether you use theta or t or who cares, you know. Let's just use t because that's more conventional, I guess. That's more the norm. But wouldn't this just be 1 minus 2 cosine t times cosine of t, and this would be the same thing, but times sine of t? It's really that easy. And then this one, what would it be? X equals 4 times sine of t times cosine of t, and boom, bam. And yeah, sometimes you can actually clean this up. Like, we could have distributed here if you want to. I guess this one was more blatantly obvious to, like, oh, sine t times sine t is sine squared of t, you know. Well, that does it for part 1, people.